Hello, everyone, and welcome back. So we continue our journey on multivariate calculus. Last class, we talked about vector algebra. Today, we are going to talk about matrix algebra. And both are extremely foundational topics for any kind of scientific discipline, be it quant finance or data science or any other thing, right? So there is a lot to this matrix algebra, but I will cover the most important ideas and properties that you will be needing going forward. Okay. There are a couple of other topics that will remain that I'll not cover today, but we will revisit that concept when we do the application. There is something called as matrix decomposition. Primarily in our world, we will use something called as Cholesky decomposition. That is something we'll cover at the later point in time. Okay, when we do the application, in that context, I'll cover the theory as well. Today, let's familiarize with the basics of matrix algebra so that you are comfortable understanding the equations that we write using matrices and how to manipulate them. Okay, with that, let's get going. All right, we can look at this later. Okay, so we understood vector as, what is a vector? Vector is a representation of a composite entity that has various components, or you can say various elements, which do not mix together, right? And yeah, that's a vector. It has multiple dimensions. Each dimension carries a number. We can call that as a coordinate or a dimension or component or anything you want. So that's a vector. Now, when we come to matrices, let's take a very simple example, okay? I'm giving you a very general idea of what a matrix is. Consider a fruit basket that can contain apples and oranges. The first fruit basket has 3 apples and 4 oranges. Second fruit basket has 4 apples and 3 oranges, right? Ideally, one fruit basket would be a vector because apples and oranges don't mix together, right? We have to keep them separate. So for the first fruit basket, you might represent that as 3, 4. For the second one, you can call it as 4, 3, right? But there has to be a consensus. What is the first number and what is the second number, right? Everybody needs to know that. So first dimension is apple, second dimension is orange. The first fruit basket is one occurrence or one instance of the general fruit basket. It can contain any number of apples, any number of oranges, right? So the first one is 3, 4, second one is 4, 3, the first dimension being apple, second dimension being orange. This is the most general way of, understanding matrices. Doesn't have to be uh, purely mathematical all the time. It can simply be data. How do you represent data? Okay. Now, so matrix is basically if you stack multiple vectors together. Okay. Look at this notation. So for example, we can have columns as the type of fruit, apple column, orange column, and then rows are the different records or instances or examples. Okay. Fruit basket 1 becomes one row vector, 3, 4. Fruit basket 2 becomes another row vector, 4, 3. Columns are apples and oranges. Okay, so this is one way of representing this. Basically, I'm stacking two vectors together. So vector 1, vector 2. That's the matrix. In the broadest sense, that's the matrix. It's just basically you're stacking multiple vectors together. Now, I could use columns, fruit basket as columns, and the apples and oranges can become rows, but that is not ideal. That is not how we encode the information in the world. If you're familiar with databases or data frames, we'll be working with a lot of data frame objects very soon in using pandas in Python. In a typical data frame or database, the columns do not change often. If you want to change a column, that requires a lot of coordination with different teams. I'm telling from a practical perspective. If you want to update a column or add a column or delete, pretty much never delete a column, then it has to go through multiple rounds of discussion with different teams, the impact analysis, then production and all these things. But rows get added left, right, and center. Okay. So yeah, I mean, if you want to, let's say you want to store the data about customer, right? Which is more dynamic that changes? Is it the customer dimension or the attributes dimension? I mean, the types of attributes, is that does that something which change too often, or the number of customers in your database that changes too often? Customers, right? So you'd rather want to delete, add rows. Okay, that's how the whole world works. Then play with columns. So if you want to build a customer database, it will be age, income, attributes as columns, and then customer ID 1, customer ID 2, all these will be rows. Okay. And you can look at this as a matrix. So each of these customer would be a row vector. Okay. And age would be a column vector. Income would be a column vector. Make sense? Any questions so far? Okay. Hope this is clear. So this is very, very fundamental. Let's move on. Okay. Now, a lot of these stuff that we will talk about today is something that you're probably familiar with from your high school days or college days, but this will be a refresher. There are some very, very, very important results that we have to remember at all times. Okay. Now, how to read a matrix or how to reference a matrix. So we have some nomenclature or naming conventions that we have to familiarize with. So in general, a matrix can have, let's say, m rows and n columns. M rows, n columns. Okay. If that's the case, we say that the matrix has a m cross n dimension. M cross n dimension. First rows, then columns. Okay. M rows, n columns, m cross n dimension. This diagonal from the top left to top to bottom right is called the main diagonal. Main diagonal, okay? And all of these elements in that main diagonal are called main diagonal entries. Anything that is not on the main diagonal is called off diagonal entries. All right. And this one is the other diagonal, as the name suggests. It's not the main diagonal, there is the other diagonal, or you can say anti-diagonal or counter-diagonal. Nobody says these ones. People typically say the other diagonal, the orange one, okay? Now, any cell can be represented as Aij. That's the universal standard of referencing any cell, Aij. Ij basically means ith row and jth column. So it's the intersection of ith row and jth column that will lead you to one specific cell that is referenced as Aij. Okay, basic stuff. Let me know if you have any questions. Okay, these are very basic, so I'll just skip it. Different types of matrices. We have square matrix. As you can guess, right? What is a square matrix? A square matrix is the one which has same number of rows as columns, right? It'll be m cross m, right? That's a square matrix. Diagonal matrix. A diagonal matrix is the one where all the elements are in the you can say off diagonal entries are 0. All the off diagonal entries must be 0. On the diagonal, on the main diagonal, there could be a few zeros also. That's not a problem. The requirement here is if it's a diagonal matrix, all the off diagonal elements would be 0. That's the requirement. That's a diagonal matrix. Okay. Identity matrix, we use this all the time. Identity matrix is basically you have ones in the main diagonal, all ones, all have to be 1. And then everything else is 0. Okay. If I equal to j, that means the value must be 1, 0 otherwise. identity matrix. Okay. Symmetric matrix. Symmetric matrix is very common in finance. We have something called as covariance matrix or correlation matrix. Both are symmetric matrix. Now, what is symmetric matrix? Aij must be equal to Aji, which means the ith row, jth column entry must be same as the jth row, ith column entry. Okay. First row, second column must match second row, first column. First row, third column must match third row, first column. And second row, third column must match third row, second column. Symmetric matrix. Lower triangular matrix. Lower triangular matrix, the condition is above the main diagonal, entries must be 0. Above the main diagonal, what is the main diagonal? This is the main diagonal. Above that, everything should be 0. Then it becomes a lower triangular matrix. Condition is if j greater than I, then it must be 0. Okay, you can see this point is row 1, column 2, right? So j, which is 2, is greater than I. I is 1. That means it has to be 0. Lower triangular matrix. Similarly, we have upper triangular matrix, which means anything below the main diagonal must be 0. That's all 0. All right. And finally, we have a null matrix or 0 matrix, which is 0 everywhere. Everywhere it's just 0. Okay. There are a lot of details in Wikipedia. If you want to, if you're interested, you can learn about it. Any questions so far? Clear, everyone? Okay. Now, we had vector algebra, right? Algebra involves sum, difference, product, and all those things. For matrices also, we have algebra, right? Starting with the simplest one, which is matrix sum. If you want to sum two matrices, the requirement is the size must be same. The size must be same. If one matrix is 3 cross 3, the other matrix also has to be 3 cross 3. Okay, and the output will also have the same dimension. So a few examples: 2 by 2 matrix, 2 by 2 matrix. If you add them, addition is very, very simple. It's element wise, just 3 plus 0 is 3, 4 plus 1 is 5, 4 plus 2 is 6, 3 minus 2 is 1. This must be same as this, and the final answer will also have the same dimension. You can add a 3 by 2 to a 3 by 2, no issues. Doesn't have to be a square matrix. The dimension has to be same. And addition is very simple. Just element by element, you just add them. And this does not work because this is a 2 by 2, this is a 3 by 2. You cannot add them. And the other idea is it is commutative. So A plus B is same as B plus A. A and B are matrices. No issues there. Okay. Next, all of these operations, ever since NumPy was created, NumPy revolutionized Python. Okay, all these vector and matrix operations are just one single command and super, super fast. Okay, we'll talk all about that later. Now, matrix product. So this is a little bit tricky, not something that I don't think you are new to this, but just a quick revision. So the two, A and B are two matrices. They can be multiplied if and only if if you look at the first matrix, N, right, must match P. They should be same. And the output, after you multiply, will have a dimension M cross Q. So in other words, the outer dimension of the first matrix must match the inner dimension of the second matrix. And after you multiply A with B, the resulting matrix will have a dimension, which is the other two, which is M cross Q. Okay. Now let's look at one example. Can you multiply these two? first thing you see, okay, this matrix is 2 rows, 3 columns, right? So 2 by 3. Second matrix is 3 by 3. Can I multiply? The only condition is this must be same as this. And it is true. Both are 3. So you can multiply these matrices. And the final output will have a dimension 2 cross 3. 2 cross 3. 2 rows, 3 columns. Okay. Now, how do we multiply matrices? One golden rule you have to remember. You know the resulting matrix dimension, right? The resulting matrix will have a dimension of m cross q. In this case, 2 cross 3. So there are 6 elements. Okay, 2 rows, 3 columns. The ijth entry in the final matrix is the dot product. The cell ij is the dot product of ith row of the first matrix, ith row of the first matrix, and jth column of the second matrix. That's how you can remember. Okay, so I have to fill up 6 cells, correct? It's a 2 by 3 matrix. I know that. This is the first cell. Row. Okay, what is the nomenclature of the first cell? Who can tell me? How do we reference the first cell? Anyone? How do we refer to the first cell of a matrix? A11, exactly. First cell. So A11, first row, and first column. So A11. That means I equal to 1, j equal to 1. If I equal to 1, j equal to 1, I need to take, remember, the ith row from the first matrix, which is the first row of the first matrix, and first column of the second matrix, because it is A11, right? First row from the first matrix, first column from the second matrix. Take these two, do a dot product. That is exactly what I've written here. 344 dot 120. Okay. Similarly, let's talk about this cell. What is the, how do I reference this cell, guys? What will it be? A 2 3. Is it 2 3 or something else? This is 1, 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 and this is 1. There are 6 elements. Okay. 2 2. Yes. Second row, second column, correct? Sorry. Second row, second column. So how do I do it? Second row, second column means second row from the first matrix, dot product. That's this one, dot. Second column from the second matrix, 1 2 minus 1. Right? So this is the first step. After you, after you identify which row, which column needs to be multiplied using dot product. Next step is easy. Just do a dot product. Dot product of the first one is 3 plus 8 plus 0. 3 plus 8, 11. And this guy would be 4 plus 6 minus 3, 7. Okay. That's it. So this is how you, so 2 things you have to remember. First of all, is the product possible? Right? The required condition is n must be equal to p. And the output would be m cross q. Okay. And then you do the product. And yeah, that's it. And remember one very important rule. You cannot swap the order of the multiplication. It is not the same. A cross B is not the same as B cross A. A cross not, I mean, A multiplied by B is not equal to B multiplied by A. In case of matrices, this is not true, not commutative. Please remember. Okay, any questions? Product, is it clear? Hernan says ith transpose. Yeah, I have not spoken about transpose, but yeah, you are correct. So you cannot actually do dot product of a row vector and column vector to be precise. But since they are of the same dimension, right? I mean, yeah. So uh, you are correct to be exact, but this is how you can find out the product. Okay. All right. When you isolate the vector, it actually loses the significance of being a row or a column. This is something you will notice in Python when working with NumPy also. If it is in a matrix, then it has a significance as a row or a column. Once you strip it out, it is just a vector. So that's why I did not talk about transpose. Um, so this is one vector, this is another vector. Just do a dot product. All right, good. Any other question? All of you are silent today. All good? Can I move on? Okay. Transpose. Yeah, the timing could not have been right. Transpose is a very useful operation, right? What it does is basically your rows becomes columns, columns becomes rows. That's all. Okay. So if you had an entry, basically the aij entry in the original matrix will appear in the jith position after transpose. So if you find it here in A transpose, you'll get it in the jith position, the same element. Rows becomes columns, columns becomes rows. All right. And you write transpose as either A T transpose, or you can write like this, A prime. That also works. So both notation. Now let's do a quick example. One, so this is my original matrix. If you take transpose, I do it like this. Take this 1, 2, 3, write it as the first column. Take the second row, write it as the second column, 4, 5, 6, and take the third row, write it as the third column. And that's it. Okay, simple stuff. There's a few useful properties of transpose. If you do transpose twice, A transpose and then transpose, obviously that will return the original matrix. A plus B whole transpose is A transpose to B transpose. That's good. K times A whole transpose. What is K? K is a scalar. A number like 5 or 2 or whatever. Multiply that with the matrix. By the way, if you multiply a scalar to a matrix, it gets multiplied to all the elements. Okay, just multiply with all the elements. So if you want to multiply 2 with the matrix, it will double all the entries. Then you take the whole transpose. Okay, that's like you can take the K outside. Just do the transpose of the original matrix, multiply K afterwards. Same thing. All right. So just as in case of differentiation, integration, K comes out. In case of transpose also, K comes out. And one more thing, if I ask you what is K transpose, K is a scalar. Normally it doesn't make sense. But if I ask you what is K transpose, what will be your answer? It's K, right? What is the transpose of 5? It's 5. There is no row, no column. It's just one single entry. You can think of this as a 1 by 1 matrix. If I tell you 5, 5, you can, picture as one row, one column. If you do transpose, it remains the same. There is no change to it. Okay, now, extremely important rule. In a lot of these derivations, this rule is used. Pretty much 95% of the derivations will involve this property. A times B whole transpose is B transpose A transpose. Please do not do A transpose times B transpose. Okay. All right. This is transpose. Any questions? All right. Let's move on. Okay. Little bit heavy stuff. Pay attention. So let's talk about determinant. We write determinant as this. You put two bars outside of the matrix. A determinant of A is equal to actually I should have written A. So A is this matrix. Determinant of A, maybe I can put a bar here. All right. For a 2 by 2 matrix, you have to remember this formula. The determinant is AD minus BC. AD minus BC. Okay. Now coming to a 3 by 3 matrix, how do you calculate is you can actually do it row wise or column wise. Typically what we do is we follow the first row. You can take any row and do it actually. Okay, maybe I'll show you that. Take the first row, look at the first element, keep it like that. That gets multiplied with, cover the column involving that element and cover the row involving that element. Whatever you are left with, which is E, F, H, I, you put it like this. Determinant of E, F, H, I. Okay. Now you move on to B. Keep B as is. There will be a minus sign. So it alternates plus, minus, plus, minus, plus, minus. Minus sign time B times determinant of, cover that row, cover that column. What do you get? D, F, G, I. D, F, G, I. Determinant of that. Then plus C again. Plus C, cover this row, this column, you get D, E, G, H, D, E, G, H. Once you have this and you know how to calculate the determinant of a 2 by 2 matrix, you have the answer. So it's A times EI minus HF. So you get AEI, that is the first term, minus AHF, which is this term. Look at the next one, minus BDI, minus BDI. Again, minus B times minus GF. So plus BGF, plus BGF. And you can do this one. You'll get these two terms. Okay. And if you have a 4 by 4 matrix, it's the same idea. Scan the first row, go element by element, alternate these signs, plus, minus, and then the determinant will be a 3 by 3 determinant. Correct? If you have a 4 by 4 matrix, then these guys will become 3 by 3 matrices. Right? And that will use this feature, the 3 by 3 matrix determinant that we calculated. Same way you can see, nobody will do it manually. I'm just telling you how it is done. You will never calculate determinant manually. There are formulas, inbuilt functions in every single software application. Excel has it, Python obviously has it. You'll never need to calculate by hand. Sambhav has a question. What is the use of determinant? Coming to that. Determinant, think of this like this. So remember vector, size of a vector. Size of the vector is like the length of the vector, right? Similarly, determinant of matrix has a size connotation. Specifically, it represents the area or the volume, depending on how many dimensions you are talking about, captured by the column vectors. I will show you that a little bit later. But determinant manifests in all kinds of calculation. If you want to solve system of linear equations, it comes there. If you want to calculate eigenvalue, it comes there. So very general notion, determinant is kind of like a size of the matrix. Okay, just as we have length of a vector, determinant is like the volume or you can say volume is a generic word, doesn't have to be in 3D. volume captured by the column vectors is how you can interpret them. Okay. It's kind of a size of a matrix, not the dimension, like how much can be contained in that matrix, something like that. Okay, so this is how you can calculate determinant. Now, for every element, for example, A, there is an associated determinant that we multiply, right? Those are called as minors. And you can denote it like this. M11, 11 means first row, first column, which is A in our case. M11 is the minor, which is the determinant of this EFHI that eventually will get multiplied with the first element. Okay, this is another minor M12 because first row, B is the first row, second column, right? So the minor of B is this determinant. So these are all minors, okay? Mij, if I write, that will be for the cell ij minor. And just so that you're following, A, B, E, sorry, A, B, C, D, E, F, G, H, I, right? If I ask you what is the minor of, say, E, what is the minor of E? How do you do it? Cover the column, cover the row. What do you get? A, C, G, I. That's the minor. Minor of E. Is minor clear, guys? Is the determinant of the remaining entries that you get by covering the row and the column associated with the particular entry. Clear? Yes, in this example, this is M2, M22, correct. Now, so I hope minor is clear. Now, coming to cofactors, cofactor multiplies a sign to the minor, either +1 or -1. See, all minors are, I mean, there is no determinant itself could be positive or negative. We don't know that. But if you see in the overall determinant formula, this sign alternates from plus to minus to plus to minus, right? We need something that takes care of that sign. And that's where cofactors come in. Cofactors are given by -1 to the power I plus j, mij. You take the minor is a determinant, right, of the remaining entries, multiply it with -1 to the power I plus j. You already know what is I, what is j. And that's it. So if you look at the first expression, A times something, the coefficient of A is 1. It is not negative, it is +1, right? How do I remember? Very simple. Just this is the formula. -1 to the power I plus j. In the first element, the I is 1 and j is 1. So I plus j is 2. So -1 whole square, which is +1. Okay. If you look at the second entry, which is -b, how did I get the -b? Because the position of b is I equal to 1 and j equal to 2. I plus j is 3. So -1 to the power 3, that's -1. That's why you get a negative sign. All right. So did you understand how to calculate cofactor? So the cofactors are the one that you need to use to evaluate the determinant. It's the alternating plus minus sign. And typically in high school, no, so cofactors specifically do not have any application. It is the determinant that is useful. There could be other applications. I'm not aware, but it's a means. Think of minors and cofactors as a means to calculate determinant. Okay. There is also another there is also something that we calculate called as adjoint. Adjoint is used in calculating inverse. For adjoint, you need to know the cofactor matrix. Okay, so I'm coming to that. Just wanted to quickly show you something. Hold on. So we have this matrix, right? Okay. And we said determinant of A is, let me write, sorry, write the expression A, E, I, B, F, G, C, D, H minus C, E, G, B, D, I, A, F, H. This is a determinant, right? Typically, we just work with the first row and we get the expression. Today, let's work with the second row. Forget about ABC, just work with the DEF, okay? So I can write A mod is D. What will be the sign of D? Think of cofactors. What is the position of D, guys? Should it be minus D or plus D? Cofactors. Minus Y, second row, first column, which is 2 plus 1 equal to 3, minus 1 equal to 3, minus 1, perfect. Determinant of cover D, the row and the columns involving D. What are you left with? B, C, H, I. Okay. Yeah. If the first one is minus, you don't have to worry. The second one will be plus, right? Because, yeah. If I cover E, what do I get? What do I get? A, C, G, I. And last one would be minus again. It's alternating. Is it A, B, G, H? Right? Now, if I expand this, what do we get? B, I minus C, H. See, 2 by 2 determinant, you know, that is very easy. You know, I'm doing A, I, C, G, F, A, H, D, G. Positive terms, E, A, I, B, G, F, D, C, H. Negative terms, B, D, I, C, E, G, A, F, H. Does it match? So that's how you can, doesn't have to, you can choose any row or any column and then use this actually not column, choose any row and just scan through that row, use the cofactors, you'll get the determinant. Doesn't have to be the first row all the time. Okay, so minus cofactors, I hope it is clear. Let's move on. Yeah, so that's determinant, minus, and cofactors. Some properties, very useful properties of determinant. We write determinant as, you can write it as DT A or mod A. See, mod means always. It's not accidental. Anything mod actually talks about size. Correct. What is minus mod minus 5? We ignore the negative sign. We just say 5. So it has to do with size. So in case of vector also, V mod, size of the vector. In case of complex number, Z mod, that is also the length of the complex number from origin. Right? So when we are using A mod, that also has to have some kind of size, notion of size. Okay. So yeah, row wise or column wise, sum product of elements and their cofactors. Adjoint of A, see, you'll never use adjoint. All these operations are already coded and available to you. You just have to run the code. It's just one time thing, okay? In case. Adjoint of A is the transpose of cofactor matrix. Transpose of cofactor matrix. You know how to calculate cofactors for every single element. Every single element. For A, for example, you can calculate the cofactor. For B, for C, for D, for E, for F, for every element, you can calculate the cofactor, right? Cofactor does not have that A. Remember, cofactor is just the sign and minor. Sign and minor. Sign and minor. Minor involves the determinant of the 2 by 2 matrix. Leaving that element alone, do not in cofactor does not include that element. When you take determinant of the whole thing, then the element gets multiplied with the cofactor. So this one is saying for every element you can calculate the cofactor, CF1, CF11, CF12, CF13, etc., etc. And you'll get a 3 by 3 matrix of cofactors, CF11, CF12, 13, right? Take the transpose, that's the adjoint of A. Okay, we'll do one quick exercise maybe. And very useful property, determinant of A times B is determinant of A times determinant of B. So that's very good. Question from someone, in cofactors, you are having M11. Yeah. There are minors multiplied by this alternating sign, -1 to the power I plus j. That's your cofactor. Okay. Determinant of A transpose is same as determinant of A. That's kind of nice. And determinant of A inverse, I've not spoken about inverse, we're going there, is 1 divided by determinant of A. Okay. So a few properties, it's probably not possible to remember all of them. With practice, you might remember a few things. The most important ones, or you can cross check. I mean, if you're running into a derivation and then you just need to cross check, you can cross check. Couple of, I think, from a maybe interview perspective, this is important. Most used result in matrices. Okay. Oh, here is a exercise. Should we do it, or you want to try it? Show that the adjoint of this matrix is this. I'll do. Okay, let's do it. So if you look at one, see, adjoint does not add. What is adjoint? Adjoint of A is the matrix of cofactors transpose. So what are the cofactors? What is the cofactor of 1, guys? Let me write that. Can we do a mental like everything in mind? First, calculate the minor, then think of the sign and tell me the answer. What is the minor of 1? Minor of 1. 45 minus 48 minus 3. But do I need to multiply -1? No, the first element is 1, 1. So answer is -3. Correct. Perfect. What is the cofactor of, sorry, minor of 2? 36 minus 42, I think. 36, 9 times 4, 36 minus 7 times 6. -6 times -1, right? So +6. Nice. And the last one, let's do it for 3 and then you can try out the rest. 32 minus 35 minus 3 minus 3. Correct. You can fill up these ones, take transpose. If you take transpose, the first row will become first column, -3, 6, -3. I hope you didn't look at this and tell me the answer. Anyways, I'm sure you got the gist, how to calculate minors, cofactors, and adjoint, and determinant, all 4. Okay, any questions? You'll never need to calculate minors or cofactors or adjoint. Also for determinant, you have a simple A simple function in Excel, in Python, everywhere. Okay, let's move on then. So coming to this topic, some of you had a question, right? Geometrically, what does determinant signify? Determinant of a matrix encapsulates the volume captured by the column vectors. Volume is a generic term, okay? So in case of 2 dimensions, you can capture an area. In case of 3 dimensions, you can capture a volume. In case of, beyond 3, you can call it a hypervolume, but volume, I mean, it's a total space captured by the vectors. If you look at this picture, A is our matrix A, let's say A, C, B, D, like this. This is our first column. This is our second column. So AB would be this vector, and CD would be this vector, correct? We know how the vectors look like in the 2-dimensional space. So these are the 2 vectors, which are column vectors of A. Now, the area of the parallelogram formed by these 2 vectors. So you repeat the same vector here, and here we get a parallelogram. The area of the parallelogram is the determinant of A. How nice. It's actually AD minus BC. So 2 vectors are capturing some area like this. That's the determinant. Same idea you can extend to 3 vectors. So if you have a 3 by 3 matrix, the first column is ADG. That's, let's say, R1. This point is ADG, X coordinate, Y coordinate, Z coordinate. BEH is R2, BEH, and R3, our third vector, is CFI, CFI. So we have one vector, another vector. In 3 dimensions, we have 3 vectors. And you complete the parallelopiped. In 3D, we have parallelopiped. So all 3 parallel sides, and you have an enclosed space. The volume of this parallelopiped is given by the determinant of the matrix. Some geometric interpretation of what determinant really is. Okay, it's about the size. All right, let's move on. Inverse of a matrix, extremely useful operation. You need it pretty much everywhere. Now, all matrices are not invertible. Okay, first and foremost. A matrix A, to be invertible, it must be a square matrix, first of all. And determinant of A must not be 0. Determinant of A must not be 0. It should be something other than 0, and it has to be a square matrix. Only then A is invertible. Or you can say inverse exists if the matrix is a square matrix and determinant is non-zero. And the formula for inverse is adjoint of A divided by determinant of A. Okay, and we write it as A inverse. Okay, so yeah, in Excel or in Python, in any software, R, you can calculate inverse, the simple command. In Excel, it is minverse. And in Python, you can do inverse also. Everything is in NumPy linear algebra module. I'll show you very, very soon. We are going there. So yeah, don't have to take this whole route. You can directly calculate inverse using the built-in functions. Do you want me to do this in Excel quickly and show you? Let me actually show you quickly so that one moment. So our matrix is 1, 2.5, my 0.5 minus 1, 2, 1, 2, 1. The neat way of doing this, see, I don't know how much you do this, but in Excel, I realize it late. But if you really want to make it presentable and scalable, even in Excel still can do a lot of stuff. Try to make named entries. So name the vectors, matrices. That way, your readability improves a lot. Okay. So I can name this as A. Whenever I click this, it'll show me A. And you know the size of the inverse would be exactly same, 3 by 3. So I highlight. Actually, with Excel 365, I don't think I need to do that. Let me try. Minverse, which stands for matrix inverse. Just pass A and it highlights the cell. Earlier, we used to press Control Shift Enter because it is a vector array operation. I did not press Control Shift Enter. I did not even select all the cells. So a lot of these, boring operational things have been taken care of with Excel 365. I just clicked on one cell. I just pressed on Enter, no Control Shift Enter anything, and it spilled the results for me. This is the result of the inverse. This is A inverse. Okay. Try it out. And definitely, if you don't have the upgrade, please upgrade your Excel. It is totally worth it. That is a lot of improvements. Dynamic arrays and lambdas. I have started using lambdas earlier in my earlier lectures. Lambdas were not there. It was very painful. In our course, obviously, spend a lot of time in Python. In Excel, also will solve a lot of things. We'll use lambdas. Okay, I'll show you how to do that later. So yeah, this is the inverse. Okay. Any questions in this operation, guys? Is this clear? And the best part is probably this is dynamic. I'm not sure. I have not tried this. Okay. Just, oh, A needs to be, A is still this. Anyways, never mind. Okay. So yeah, that's how you calculate my matrix inverse. A few important properties. A times A inverse or A inverse times A leads to identity matrix. Remember what is identity matrix? 1, 1, 1, 1. Everywhere else it is 0. Sometimes people write matrices like this. If it is 0, they don't even write 0, just blank. And you are supposed to understand it is 0 everywhere else. So yeah, A times its own inverse or A inverse times A. By the way, if you invert it twice, what will you get? It's a very simple, trivial operation. Invert a matrix twice. What will you get? You'll get A back. Okay, cool. All right, so A times A inverse is identity. Scalar times A, whole inverse is scalar comes out as 1 by k. Please don't take it out as k because we are doing inverse. What is inverse of 5? It's the same understanding that we have, right? 1 by 5. So it comes out as 1 by k and then A inverse. AB whole inverse is B inverse A inverse, similar to transpose operation. Please remember the order changes. B inverse A inverse. There is a typo here. This should be transpose. A transpose whole inverse is A inverse whole transpose. I will correct this and share with you. Okay. So that's inverse. Inverse is extremely important. Why? Because a couple of, those who are interested for use case, right? In case of solving system of linear equations that we will do a little bit later, you use matrix inverse. And also, for example, multivariate probability normal distribution. Multivariate normal distribution, the PDF of that involves an inverse of the covariance matrix. So we'll cover that shortly. Right after the multivariate calculus, there is one more thing left to do, which is probability. And that's it. We will be done with primers. We can start our Python journey. All right. Now, special matrices. Okay. Uh, if A transpose is same as A, that's a symmetric matrix. All right. You remember in symmetric matrix, we have the ijth element, which is same as the jith element, and transpose operation precisely takes the ijth element and puts it in the jith place. Okay. And if after transpose it is the same as A, that means it's a symmetric matrix. If A transpose is minus A, it's called a skew symmetric matrix. See, for our purpose, primarily, which matrices are important? This is very important. This is a little bit important here and there, not as important as symmetric matrix. So what is orthogonal matrix? Transpose is equal to inverse. Transpose is equal to inverse. And idempotent matrix is you keep multiplying A with itself, you keep getting back A. A times A is A times A times A is A to the power 4 is A to the power 100 is A, idempotent matrix. If the determinant of A is 0, it's called a singular matrix. This is dangerous, right? You have to be careful whenever, anytime you hear the word singularity, it is a dangerous thing. Okay. If determinant is 0, it is singular. Now, these two are also important. Please understand. For any matrix A, if X transpose AX is strictly positive for any X, X is a vector. X is not a scalar. Please remember, there is a transpose. For any vector X, all right, X transpose AX is positive. You take any vector X. X should not be 0. Like, you should not have X as this. Then obviously, how will this be positive if you're taking 0? Take any X. For any X, if this is strictly positive, then it is called as positive definite. It is I mean, it's very likely that you will be asked this question in interview. Okay. And if it is greater than equal to 0, that means for some cases it is coming as 0, for other cases it is positive. Then we call it positive semi-definite. All right, for non-zero X. Our covariance matrices or correlation matrices need to be positive semi-definite. Ideally, they should be, but because of data issues, estimation error, and all kinds of technicalities, sometimes we end up with matrices, covariance matrices, which are not PSD. And there are treatments to correct that behavior. We'll talk all about those when we discuss Cholesky decomposition later on during some practical application. I'll walk you through the whole story. Okay, so just remember the definitions for now. Any questions on this slide? Clear. Okay, let's move on. All right. So probably after this, we can take a break. So this is very, very important. Let's talk about column space, row space, and rank of a matrix. Now remember, in case of vectors, we discussed about vectors being linearly independent. Remember? If two vectors basically replicate the same direction, for example, then they are dependent. If there is some non-zero angle between them, then they become linearly independent. Now, the way you can verify this, so let's say there are three vectors, this, and this. Are these linearly independent? How do you verify that? We did all of these exercises last time. But there are two ways to showcase that three vectors are not linearly independent, or they are linearly dependent. How do you show that? One way is, can you synthesize or replicate one vector as a linear combination of the other two vectors? If this is the case, then these three vectors are linearly dependent, right? So this is one way. You can see that this is 1 plus 2, which is 3, and then 2 plus 3, which is 5. So I can create 3, 5 out of 1 and the first two vectors using a linear combination of them. These are the scalars that we are multiplying, alpha, beta. Remember, alpha v1 plus beta v2 leads to the third vector v3. The other way of doing this is, if you can showcase that a linear combination of all three leads to zero vector, null vector. So just rearrange, right? So 1 times 3, 3, 5. Take these guys to the left-hand side. You get times 1, 2, minus 1, 2, 3 is a zero vector. Then also that means that it's linearly dependent. Okay. Now, when we write matrices, remember first definition, matrix is a stack of vectors. If you look at all the rows, these are row vectors stacked together. If you look column wise, we have column vectors stacked together. Now, since we have multiple vectors in a matrix, we can talk about the span of those vectors. Consider row vectors. Are they independent? What is the span of the row vectors? That is called as the row space. Similarly, if you look at the column vectors, what is the span of the column vectors? How many are linearly independent? How much space is described by the combination of those vectors, right? Is it just a line or a 2D plane or a 3D space? We'll talk all about that. That's the column space. So column space is the span of the column vectors of a matrix. Row space is the span of the row vectors of a matrix, which will be same as the column space of the transpose of the matrix. That's trivial. Okay. Now, here is something important. There is a little bit of ambiguity in which the literature describes rank. Typically, if you have a square matrix, right, the number of linearly independent vectors is the rank of the matrix. So if you have a 3 by 3 matrix, for example, are all three vectors, row wise, column wise, doesn't matter, are all three vectors linearly independent? Then the rank would be 3. Or is there one redundancy? So two vectors are linearly independent and third one you can manufacture using the first two. Then the rank becomes 2. Okay. And if the highest rank that is possible is what you also get in the matrix, then it's called as a full rank. So a 3 by 3 matrix, if it has 3 independent, linearly independent vectors, it will be called as a full rank matrix. That means the highest rank that is possible, you achieved that. Okay. If it is a non-square matrix, then you can, 3 by 2 matrix or 4 by 5 matrix, then you can calculate a rank for the row, taking the row vectors, and also another rank taking the columns. Okay. And whichever is higher, you can call that as the rank of the matrix. It's a little, there is little ambiguity there, but it's fine. I have some examples, it will be clear in the next slide. But yeah, rank of a matrix is the number of linearly independent vectors. Okay, if it is a square matrix, it does not matter if you look column wise or row wise, it will be same. That is the beauty of it. If it is a square matrix, you can just look at the columns and see how many of the column vectors are linearly independent. That's the rank of the matrix. Okay, this is what I've written. Row space is equal to columns. Again, what is space? Space is the span of those vectors. Okay, what space is what is the coverage of the space? Remember, we talked about this. If you have one, so in two-dimensional plane, if you have one vector like this, another vector like this, same direction. What is the span? Span is just this line. You can never get out of this line. Take any linear combination of these two, you'll roam around on this line. Span is one dimension, 1D. Okay. But if you have some non-zero angle between the two vectors, then yeah, if this is the case, what is the span of these two vectors, guys, in two-dimensional space? What is the span of these two vectors, v1 and v2? If I take various linear combinations, what kind of space I can cover or reach? R square, exactly. The entire xy plane I can cover. You give me any vector, I can reach there using the linear combination of these two vectors, I can reach. Okay. Right. So rank of a square matrix is equal to, rank of a square matrix is equal to number of linearly independent columns or number of linearly independent rows. Both are same. It'll give you the same answer. Okay. And finally, if a square matrix is, so this is beautiful. If a square matrix is not full rank, that means if you have a 2 by 2 matrix and two vectors are not independent, determinant would be 0. Determinant 0 means singular. Yes, you're correct. Singular matrix. If a matrix is not full rank, determinant will be 0. That is a powerful, powerful result. Okay, there is one redundant vector or more. And yeah, exactly. Sachin says it will be non-invertible. Yes, determinant is 0, so you cannot, inverse does not exist. If determinant is 0, inverse does not exist. Now, to understand all of this, let's go through these examples one by one, and then we'll pause for a break. But this will make you confident on the subject matter. Let's go through this. So we will, for various matrices, we'll find out the column space, row space, and the rank. Okay, I've written everything here, but let's think first. Do not refer to the answer, just think. Look at the first one. This is the, a very fundamental matrix, right? What kind of matrix is this, guys? Quickly, what kind of matrix is this? It's a 2 by 2 matrix, but it has a name. Not unity, we call it identity matrix, denoted by I. Right? Cool. Now, if you look at the, let's do the column space. Column space is this. This is one vector, this is one vector. So one vector is 1, 0, the other vector is 0, 1. Quickly, in 2D space, these are the unit vectors. Unit vectors. So 1, 0 is this, 0, 1 is this. Using these two, how much space can I cover? What is the span of these two vectors? First of all, are these linearly independent? Are these two vectors linearly independent? Of course, they are linearly independent. They are orthogonal. That's the best kind of linear independence you can have. This is the best kind of linear independence. Okay. Movement in one direction does not affect the movement in the other direction. They are completely, completely independent. So you can span the entire R square space, right? 2D space. So for this one also, 1, 2, 3, 4, these are non-standard, as in not unit vectors, but they also have some angle. 1, 2 is like this, 3, 4 is like this. So you can span the entire space. So the column space is whole of R square, okay? Entire XY plane. Look at the row space. Row space would be like this. Take this vector and this vector. Again, 1, 0, 0, 1. So no difference. If you look at this 1, 3, 2, 4, slightly different vectors, but still independent. Independent, right? Both vectors are linear independent. So the row space is also entire R square. Rank of this matrix would be 2. Why 2? Because there are two linearly independent vectors. Two linearly independent vectors. So rank is 2, and it is called full rank because the size was 2 cross 2, and I could achieve the highest rank possible. So it is full rank. Okay. Is it clear? The first one? Any doubts? Okay, cool. Look at the next one. This is a rectangular matrix. It's not a square matrix. So technically speaking, we can have two possible ranks, one from row using row vectors and one using column vectors. Now let's look at the column space. 1, 2, 3, 4, right? 5, 6. Now remember, if you have a two-dimensional vector, right? Maximum number of linear independent vectors that can exist is 2. Beyond 2, you cannot create additional vectors. That has to become a linear combination of the other two. This is what we discussed earlier, right? So if you look at column space, is it able to span the entire R square or not? Yes, these two are linearly independent. They can span the entire R square. The third one is redundant. Or you can say out of the three, two are linearly independent. The third one, whichever you choose, can be replicated as a linear combination of the first two. So out of three, two are independent and one is dependent. Make sense? However, as long as you have two independent vectors, right, in 2D space, you can span the entire R square. Okay. Now let's look at row space. For the row space, we have these two vectors. Now these vectors are three-dimensional vectors because they have three coordinates: 1, 3, 5, 2, 4, 6. We're talking about 3D space. One vector is like this, maybe another vector is like this. Okay. So what is the span of these two vectors? Span of two vectors can be maximum a 2D plane. It is the plane consisting or held by these two vectors. Hard to imagine, I know, but how can I describe this? Um, yeah, think of a plate. Think of a plate that holds these two vectors on the surface of the plate. So take your food plate, put two arrows or chopsticks or whatever, okay, and rotate that plate so that, the two chopsticks are these two vectors, and then the plate becomes the plane that is spanned by the two chopsticks. Okay, so two vectors hold a plane. They cannot hold a 3D space. Two vectors cannot enclose a 3 volume. They can only enclose some area or the plane that contains the two vectors. Okay, simple example, xy. Xy contain a plane, right? Xy contain the xy plane. So just pretend these are my new xy. Just forget about the original coordinate axis. Two vectors. One is x, one is y. That will contain a plane. Okay. So yeah. So the row space would be a 2D plane in R cube. Make sense? R cube is my original space, but am I able to reach every single vector? No, you cannot. You are constrained in the plane contained by the two vectors. You can only move in that plane. You cannot come outside of it. Okay. Let me try to draw. Maybe I'll try. I'm not, because 3D is always challenging, right? Um, one vector like this, one vector like this. I mean, it's not easy to draw. Just think of a paper, or let's do this. Picture a kite in the sky. We live in a 3D space. Our world is 3D, right? Picture a kite flying in the sky. We have these two sticks. Or let me not draw it curved. Now, it doesn't matter how the kite is in the space. It can take any orientation. That doesn't have to be flat, staring at you. It can be slanted, horizontal, vertical, whatever. Two sticks are contained in that kite, which kite is a plane. Kite is not a 3D space. Does that make sense? So whole kite is in a 3D space, but the two vectors constitute a plane, which is the kite surface. And you can turn the kite any direction, doesn't matter. But two vectors which are independent can contain an entire plane. In this case, the kite is the plane. Make sense? Cool. Right. So the space is RQ because this is a three-dimensional vector. But these with two vectors, you can maximum describe a 2D plane. So that's the row space. Now, if you talk about the rank of the matrix, this is little complicated because it's a rectangular matrix with two rows. You can maximum span a 2D plane, and that is what we are doing. So it is a full row rank. But with three columns, Ideally, you should be describing a 3D space, a R cube, but you're not doing that. You're only describing R square. So it is not full rank from a column perspective because you have three columns, but you're only describing, there are only two linearly independent vectors. But you have two rows and both two rows are independent. So it is full row rank, but not full column rank. Okay. And if somebody asks what is the rank, you say two. Two, whatever is the highest rank that you get, either row wise or column wise, that's the rank of the matrix. Yeah, for rectangular matrix, it's not that neat, but for square matrix, is just very, very straightforward. You can take the row space or the column space, doesn't matter, both will be same for a square matrix. Let's look at the next one. Look at this matrix, 1, 1, 1, 1. How many linearly independent? What is the column space? This is one column, this is the second column. Are these repeating vectors? Are these independent or dependent? These two vectors, column vectors. Is the same vector, they are dependent, right? So two vectors which are two 2D vectors which are in the same direction, essentially they're the same vector. The span is just a line, right? Same vector. So the span would be this line. It cannot cover the whole 2D space. Okay. So a line in R square. Same case here also. One vector is the double of the other vector, right? So we have one vector 1, 1. The other one is this one 2, 2. Just, redundant, right? So linearly dependent, they are linearly dependent. Column space would be line in R square. Row space would also be a line in R square. If you see 1, 1, 1, 1, 1, 2, 1, 2. Again, line in R square. Rank would be 1. Rank would be 1 because how many linearly independent vectors are there? Only one. So rank is 1. Is this matrix full rank, guys? Is this matrix full rank? No. Correct. Okay, hope this is clear. Move to the next one. What is the column space? This, this. Are these three vectors linearly independent? Yes, no. Are these vectors linearly independent? Mridul says they are not. Why? Yes, that's correct. If you add the first two, you get the last one, right? Or you can say if you subtract the second one from the third one, you get the first one. So there is a perfect linear combination that exists. And there are how many linearly independent vectors? Two. So if you take column space, in ideally there are three column vectors, I should have been able to span the entire XYZ plane, XYZ space. But because there are two independent vectors, I can maximum span a 2D plane in R cube. Okay, the same kite scenario. And in row space also, remember for a square matrix, it's very simple. Both will be same always. 2D plane in R cube. Rank is 2, it's not 3 because there are two independent vectors. Okay, if you look at row wise also, we have 1, 2, 3, 1, 3, 4, and 1, 4, 5. Is this still linearly, like how many linearly independent rows are there? It's hard to see. If you do this plus this and then divide by 2. So 0.5 times the first row plus 0.5 times the last row is the middle row, right? So anyways, okay, so that's, rank is 2. This, is this clear, guys? Did you understand this? It doesn't matter, row wise, column wise, if the number of linearly independent vectors will be the same if it is a square matrix. Okay, let's move on. Next matrix. What is the span of this matrix? It's a zero vector everywhere. I mean, row wise, column wise, there are just two zero vectors. With zero vectors, can you go anywhere? You're stuck at the origin forever. No matter how much you scale, you cannot scale a zero vector, it'll still be zero. Adding zero vectors together will still be zero. So you will never leave the origin. The space that you are able to span is just a point, which is the origin. Point in R square. It's a zero rank matrix. Okay? Because it's just a point. Next one. This is beautiful. This is identity matrix in 3 dimensions. And everything is like orthogonal, full rank, R cube. Makes sense? There are no linearly independent. I mean, yeah, sorry. All 3 are linearly independent vectors. Let's look at the next one. 2 by 3 matrix. If you look at the column space, you know for a fact that column space cannot be a 3D because these are 2D vectors, and maximum space you can get out of 2D vectors is a plane. But you can do worse. You can, instead of 2D, you can have a line, and even worse would be a point. So let's see. If you look at the 3 vectors, how many linearly independent vectors exist? Look at the column vectors. How many of them are linearly independent? Riddle says 1. Anybody else? It's 1. That's correct. Because using 1, 3, I can generate 2, 6. Just multiply by 2. And 3, 9. Multiply by 3. So there is only one fundamental vector, and others are just replicas, scaled version of those. Right? So really speaking, there is only one vector. If you look at the 3 vectors, there's only one linearly, I mean, it's just one, it's independent. Others are dependent on it, correct? So same vector being replicated thrice. So 1, 3, 2, 6, 3, 9. Okay. So any linear combination of these 3 will still keep you in that same direction. So it's just a one line in R square. And if you look at row space, it's still one line because the second vector can be created from the first one. Just multiply 3. So there is only one vector. If there is one vector, you can get only a line in R cube, mind you, because in row space is a 3-dimensional vector. There are 2 3-dimensional vectors, but both are in the same direction. So you can span a line. Okay. And in both cases, I'm getting a line, so rank is 1. Okay. Finally, let's look at this. There are 4 column vectors. 1, 2, 3, 4. I can see that the first one and the last one are independent. So that means that I'm covered. Maximum I can span a 2D space. I do see there are 2 independent vectors. I can cover the whole R square. If you look at the row vectors, this and this, are they independent? Yes, because 1 times 3 is 3, 2 times 3 is not 4. So they are independent. With 2 independent vectors, with two independent vectors, you can span a two-dimensional space, which is a plane, right? It will be a plane in R4 because the row vectors are four-dimensional vectors. So just picture a R4 space. I don't know how you can do that. It's not possible to think of a four-dimensional space. Whatever it is, in that space, the row vectors can span a plane. Okay. And rank would be 2, because the highest rank from the column space is also 2D, and from the row space is also 2D. So the overall rank is 2. It's a full row rank because with two row vectors, I can maximum get a 2D plane, and I got that. So it's a full row rank. But with four column vectors, I should ideally generate a four-dimensional space. I could not. I only generated a two-dimensional space. So yeah, that's it. Any questions before we pause for a break? Row space, column space, rank. Is it understood, guys? Okay. All right, great. So let's take a 5 minutes break and then we'll continue with the remaining stuff is more application oriented. So it's every day's requirement. Yeah. So let's meet after 5 minutes. All right, let's move on and look at some of the fun applications of matrix. Okay. Starting with the most interesting one. Just a quick audio check. Can you guys hear me? Okay, awesome. Let's look at what happens when you multiply a matrix with a vector. Okay, multiplying a matrix with a vector. So here is our vector x. We multiply a matrix A times x. That will give us another vector. So see, what is the dimension of a vector? It is n rows, one column, correct? Dimension of a matrix A. So n has to match. So let's say it is m cross n. All right. If you multiply, can I multiply first of all? Yes. These two are matching, so I can multiply. The resulting vector B would have a dimension m cross 1. M cross 1. So this is also a vector. I just wanted to show you that if you multiply a matrix with a vector, you get a vector. M rows, 1 column. Okay. And if A is n cross n, a square matrix, then you will get the same size of vector, n cross 1. So that's nice. So you multiply a matrix with a vector, you get another vector, which is a transformed vector. Okay. Now let's look at what happens when we multiply. There are two ways to look at it. So let's say this is our A matrix, and our vector is a flexible vector xy. Notice small things. Bold X is for vector. Bold X is vector. And the regular xy are the components or elements of that vector. Okay, xy. So individually, these are scalars. And together, they form the vector x, which is in bold. All right. And what is B? Guys, give me 1 second. 1 second. Okay, yeah, sorry about that. B is product of A times X, right? Now we know how to multiply this. One is the dot product method that we talked about initially. That is the row picture. Okay, you look at the the rows individually, so you know that the resulting and the outcome is a vector, right? So what is the first row? First row is 5 times x plus 2 times y, 5x plus 2y. And the second row is 1 times x plus 3 times y, which is x plus 3y. So you look at row by row. That's a row picture or a dot product picture. Okay. This is fine. But there is another way to look at it, which is the column picture, or you can say column space. And this is very, very useful. I can rewrite the same thing like this. X times first column plus y times second column. Okay. Now just verify that these two are same. So if you multiply a scalar to a vector, the whole vector scales, right? It'll be, so this will be 5x and x, and this will be 2y and 3y. And then you do add. If you add two vectors, it's just 5x plus 2y and then x plus 3y. Same thing. But the representation is different. But this is much more elegant. You know why? Because this is a linear combination of two vectors. This is v1, this is v2. X and y are scalars, correct? Because x and y are just scalars. So x times v1 plus y times v2. So what we are looking at here is the result, which is b, is just a linear combination of the column vectors of A. B is a linear combination of the column vectors of A. And what do we call the linear combination of the column vectors of A? The column space. It is the space that is captured by the column vectors of A. So if B is produced by a linear combination of the column vectors of A, that means B must lie in the column space of A. B must lie in the, whatever space these two vectors 5, 1 and 2, 3 are able to achieve, any space that you can create, right? And those space, the different vectors that you can create out of this is based on choice of xy. That is fine. But there is a column space, right? That's the two-dimensional space that is spanned by these two vectors. And B is a linear combination of these two vectors. So B must be present, or B can only be, that's nice. B will be in the column space of A. It will not be outside of the column space of A. This is a powerful result. Makes sense? So whenever you multiply this matrix with any vector, the resulting vector will always be in the column space of A. Which means if the column space of A is R square, then the resulting vector can be anywhere in R square. It will be a two-dimensional, it can be anything in the XY plane. If the column space of A is a line, if the column space of A is a line, that means you have a repeating vector. So let's say 1, 2, and 2, 4. Remember the column space, because these vectors are repeating. It's just, there's only one linear, one vector which is independent. The column space is not R square. It is just a line. 1, 2, 2, 4, same in this line. So anything you multiply here, the resulting vector will be on this line always. It cannot be outside like this or anything. This is powerful stuff. Make sense? Vector transformation of vector transformation by multiplying a matrix leads to the transformed vector, which will always be in the column space of the matrix. So depending on how general the column space is, the kind of vectors that you get out of the matrix multiplication would be either, constrained to that space, is basically what I'm trying to say. Final vector will be constrained to the column space of A. This has far-reaching implications, okay? Now let's look at the applications. Before this, let me show you a little bit of animation, so that you're not, sleeping. We have very, very special types of matrices that do all kinds of transformation. Okay. So for example, this is my original vector x. Let me not write like this. This is my x. After I multiply a to x, what does it become? It becomes b. But how does b look like? I can get all kinds of transformation, starting with no change, b equal to x. When this will be, guys? Any ideas? A transform vector which is exactly the same as the original vector. When will that happen? Any ideas? What does a have to be for the transformed vector to be exactly same as the original vector? Under what condition b is equal to x? If a equals to identity. Yes, exactly. If a equal to identity, there is no change to x. You can verify that. 1, 0, 0, 1, x, y equals to x and y. Just multiply quickly, verify. If A is identity, there is no transformation. So choosing different kinds of A gives interesting results. Let's look at some animation. Okay. Sometimes the Excel is not able to handle the stress with the recording and everything going on, but I hope this will work. Okay. So here on the left-hand side, you have the original space. On the right-hand side, we have the transformed space. Now I'm using the word space, which basically means the span of the vectors or vector space, we can say. We will focus on one specific vector. Right now, this is 1, 2, you can see. And the matrix that I have multiplied with x, a times x leads to b here. Right now, this is identity, so there is no change to x. So b is still 1, 2. Okay. So that is what you see here in the picture. Original vector, multiply with a, you get b, which is exactly 1, 2. No change. Okay. Now, this is one specific vector, but it is helpful to think in terms of entire vector spaces. That means I can choose any other vector. If I choose, say, 2, comma 3, 2, comma 3, right? That also remains unchanged because it's the identity matrix. I'm multiplying the identity matrix to the x. It is unchanged. Now, I'll try to, play with A, okay? What happens when I make this as 2? This leads to stretching along the x direction because I only change this particular value, not the other one. So you see that there is, guys, give me 1 second, please. Okay, sorry about that again. Yeah, so if I change this, it leads to stretching along the x direction. If I change this, it leads to stretching along the y direction, maybe a bit too much. Right? So now you can feel when I say transformation of vector spaces, this is only one, this is our protagonist vector, right? But you can pretty much take any other vector and that will be transformed in a similar way. 2 times stretching along x-axis and 3 times stretching along y-axis. Make sense? You see how it is getting transformed? Now, there is some lag in the calculation. Let me, yeah. Okay, let's go back to, all right. You can do a lot of things. You can do So there is a matrix that causes, so we understood stretching, right? Now we can work on, we can talk about, say, reflection, for example. If I make this -1, it creates a mirror image of the vector along x-axis. You guys are still there, right? Can you hear me? Okay, cool. This is a reflection. We also have, there are a lot of, we have a shear matrix, we have a permutation matrix, we have projection matrix, we have rotation matrix. Let's do rotation. For rotation, let's say you want to rotate a vector by 45 degree. Okay. The rotation matrix is given by this: cos theta minus sine theta, cos theta. Theta is 45 degrees. So if I calculate all these values, this is your rotation matrix. If you multiply this matrix with this vector, it will rotate by 45 degree. In fact, let's try with 1, 1. It will be better. If I rotate this by 45 degree, what will happen? Let's see. There is some lag. 1 second. We'll fix that. Right? So it will coincide with y-axis. That is what you have seen. The whole space has been rotated by 45 degrees. X coordinate is almost 0, 10 to the power minus 16. This is numerical error. And the whole thing is in, what is the length of this? Length of this is √2, right? Square root of 2. Square root of 2 is 1.414. That 1.414 is this length, which is completely along y-axis, because this is 45 degree. If I rotate this by 45 degree, it will completely align with the y-axis. Right? This is the rotation vector, rotation matrix. So with various, choice of, there is a permutation matrix also. Wait, let me try to. So we have identity. If you swap the, I think this is 0, this is 1, and 1, 0. Right. This is called as a permutation matrix. So what has happened is you have swapped the order. 1, 2 has become 2, 1. This is nice. And you can see the entire space being transformed. Look at the space. Earlier, the grid was like this. Now it is like this. All right. So this is what matrix does to a vector. Okay. Geometric interpretation. Happy with this? Any questions, any doubts on this? All right, let's move on then. Okay, now, what is the application of this? The first important application is solving a system of linear equations. We have done this back in our high school. If you have two equations like this, two equations, two unknowns, you can solve them. If it becomes 15 equations, 15 unknowns, then it'll take forever for you to solve it on paper, right? There'll be silly mistakes, lot of silly mistakes here and there. Anyways, so we have softwares to take care of that. You elegantly solve the system of linear equations using matrix. So how do we rewrite this equation using matrix is write it in terms of Ax equal to B. Okay. B is this vector. A is this matrix. Is just collect the coefficients. And so here it is 1 and 3, 5, 2, 1, 3, multiplied with the vector xy, which is our vector x. That's something we need to solve. Equal to B. B is the stuff on the right hand side, 9, 7. How do we solve? So the whole thing has been rewritten using matrix and vector notations. Please understand that the unknowns are a vector and the stuff on the right hand side is also a vector. And if you collect all the coefficients and put it, it will be a matrix A. So this is Ax equal to B, which is what we just looked at. right? We are multiplying a matrix with a vector. Vector is unknown that we want to solve for. B is known. So essentially, the trans is like this. A is given. The transformation matrix is given. The transformed vector is also given. You need to find out the original vector. Which vector got transformed to become B, given A? That's what you need to solve for. Okay? How do we solve this algebraically? It's very easy. So do one thing. Multiply A inverse on both sides. And please remember one thing. Whenever you do matrix multiplication, it is not just randomly multiplying stuff on the left-hand side, right-hand side. Order is paramount. Order is important because remember, matrix multiplication is not commutative. So we use the term pre-multiply. Pre-multiply A inverse. What I'm saying is, if AX equal to B, don't do this. Multiply B here and then multiply B here. This is wrong. This is post multiply. This is pre multiply. Can't do that. It has to be unique. The same on both sides. So pre multiply A inverse on both sides. A inverse times A becomes identity. Remember, A inverse times A becomes identity times X is equal to A inverse B. Okay, so X is A inverse B because you multiply identity with X, it remains as X. We just saw that. Multiply identity with any matrix or vector, does not matter. It does not change anything. It remains the same. So left hand side is X equal to A inverse B. And this is the solution. I can solve the vector X directly by doing a simple matrix multiplication. I have to find out A inverse and B is given, and that's it. Now, naturally, for the solution to exist, A inverse must exist. Okay? For A inverse to, okay, so X is unique, the answer for X exists, one unique answer for X exists if A inverse exists. For A inverse to exist, you need the determinant of A to be not equal to 0. That is the first condition. You have to check whether A is invertible or not. If you want a unique solution for X, then determinant of A must be non-zero. And in our case, what is the determinant? 5 times 3, 15 minus 2 is 13. So cool. I know for a fact that there is a unique solution. Okay. There are so many things going on here. Okay. Did you notice one thing though? Remember, 9, 7 is a vector that must lie in the column space of A. Question 1, is A full rank? Is A full rank? A is full rank? There are two linearly independent vectors. If A is full rank, the space that it can cover is the entire 2D space, right? Entire 2D space. That means the B can be anywhere in the 2D space, which means instead of 9 and 7, I can take anything and I can solve. Even if it's, instead of 9, 7, if it is like 1, 2, or 15 minus 33, still solvable. I can reach every single point in 2D space. I can reach every single vector in 2D space thanks to A being non-singular, in this case, full rank. Right? So you know unique solution exists if A inverse exists. A inverse will exist when A mod is non-zero. A mod non-zero means all vectors are linearly independent. Please remember, if you have even one vector that is dependent, determinant suddenly becomes 0. If a matrix is not full rank, determinant is 0. Remember that. If a matrix is not full rank, determinant is 0. Everything is connected. Okay. Determinant exists means matrix is full rank. If matrix is full rank, that means I can reach any 2D space. Doesn't matter what you have here, it is solvable. There is no issue with B, it's just getting multiplied. The issue is if the A inverse, uh, you know, existing. So I hope this makes sense. And yeah, calculating A inverse is super easy in the software. You just do call the built-in function and then multiply B. So if A is this, we calculated A inverse as this. In Excel, you can do that in one shot. And finally, your solution X is A inverse times B. And this is the solution 1, 2. You can verify 5 plus 4 is 9 and 1 plus 6 is 7. Okay, same steps I have done in Excel. I can share that. Here it is. So you rewrite the equation like this, figure out what is A, figure out what is B, right? Find out A inverse. This was this Excel was done 2 years ago. So at that time there was no, I think, this spill dynamic array and all that stuff. So I had done it the old way by selecting all this. So you don't see a spill actually, but you can, yeah. So find out A inverse and then multiply A inverse times B. A inverse times B. For multiplying matrices, we have this function called mmult, and you pass the A inverse here and B here, you get the answer 1, 2. Okay. For determinant also, we have a function called matrix determ, and that gives determinant. Okay. Straightforward. Any questions? And please remember, A has to be a square matrix. Because to solve two equations, to solve two unknowns, you need two equations. And that will become a square matrix, 2 by 2. If there are three unknowns, you need three equations. It will be a 3 by 3 matrix, right? And yeah, to be invertible, first condition is it has to be a square matrix that you need to have. Otherwise, you cannot solve them. Okay. So if A inverse exists, yeah, solution exists for all B. Determinant of A not equal to 0 means matrix is full rank. Clear, guys? Okay, perfect. Now let's move on. Now this is a schematic you have to remember. So if a system of equations, so this is the definition. If a system of linear equations have at least one solution, it is called consistent. That means equations are consistent with each other. No equation is violating the other equation, right? So if a system of linear equations have at least one solution, it is called consistent. If there are no solutions possible, not even a single solution possible, it's called inconsistent. Now, within consistent, there are two possibilities. One is unique solution or infinitely many solutions. Both are within consistent. Remember, at least one solution means consistent. So unique solution or infinitely many solutions, both are within consistent. You will have a unique solution if the determinant is non-zero. That is just what we saw, right? If determinant non-zero, you get a unique solution. Matrix inverse exists and you multiply, you get one answer. There is no other ambiguity or anything. If and in both other cases, so in case of infinitely many solutions, also no solution, the determinant will be 0. Determinant of A would be 0. Okay, so if the determinant of A is 0, then you have two possibilities. Either you have infinitely many solutions or there are no solutions. Now let's look at some examples. Couple of examples. If it is unique solution, you know in one shot, find the determinant, and if it is non-zero, then you proceed A inverse B, that gives you the answers. End of story. If the determinant is 0, then you will think, okay, does it have infinitely many solutions or no solutions? So let's find out. And you probably know this. When it will have infinitely many solutions? When you have something like this. You have, let's say, x plus y equal to 2, for example. And then same equation you repeat. 2x plus 2y equal to 4. Right? You can clearly see that you have linearly, dependent vectors because you are repeating the same equation. One is a scaled version of another equation. And on the right hand side, it should also be scaled appropriately so that the equations are consistent. But since effectively there is only one equation, it's not two independent equations. One is dependent on the other. They are replicating each other. You will have, question to you, do you think you will have no solution or infinitely many solutions? No solutions or infinitely many solutions for these two? Many solutions, right? Because these are effectively only one equation. So just take this x plus y equal to 2. What is the solutions? The way we write the solution to this is you assume x as some parameter a, and then y has to be 2 minus a. So the solution is a 2 minus a. That's the solution for x, where a is a free parameter. For any, put any value of a and automatically y adjusts so that the equation is satisfied. And you can choose any a, so there are multiple, infinitely many solutions. Okay. Question, are these two equations consistent? Yes, no. Is it consistent? Yes, it is consistent. Correct. And determinant would be 0. In case of infinitely many solutions, determinant would be 0. You can check 1, 1, 2, 2. Determinant is 2 minus 2, which is 0. How nice. Everything fits together. Okay. Now, the same equation, I'll do a little bit of modification. X plus y equal to 2x plus 2y equal to 3. What is the outcome of this? Is this system consistent or inconsistent? Inconsistent, exactly. You can clearly see these are violating each other, right? Yeah, there will be no solutions. And the determinant is still 0. 1, 1, 2, 2 is the other case, okay? Determinant is still 0, but the system is inconsistent. Now look at the, let's do the exercise. Look at the first problem. What is the answer to this? You just need to stare at it and you can tell me the answer. You don't need to do any calculations. Perfect. Others, please participate. Consistent and infinitely many. Perfect. Second one. It's easy. Let me write inconsistent. No solution. Is this clear, guys? And remember this flow chart, okay? Important. All right. Now let's address the elephant in the room. This is extremely useful. Okay, the next topic. It has to do with eigenvalue and eigenvector. Now, what is all this eigenvalue, eigenvector? It has many applications in data science and quant finance. Given, okay, so we understood that when we multiply a matrix with a vector, it transforms it. Okay, it can rotate it, it can stretch it, it can perform a reflection, it can do all kinds of things. Okay, now we want to know that given a matrix A, what is the vector that only gets scaled? if you multiply this matrix to a vector, it scales that vector. See, there is a scalar multiplier with the vector. We want to know, given a matrix A, right, what are the vectors which only get scaled when you multiply the matrix with that vector? Okay, there is no change in direction. The direction remains intact. What are those vectors? And the related question would be, okay, so those are the vectors that only get scaled. The next question would be, by how much? What is the scale factor? So we are trying to address two things here. What are those vectors which only get scaled when you multiply this matrix with those vectors? Second is, by how much they get scaled, right? So look at this equation. There are two things we need to figure out. Given A, only A is given. So we want to find out eigenvalue, eigenvectors for a matrix. Given the matrix A, what are the V's which only get scaled? You can see on the right hand side that is getting scaled. Those are called eigenvectors. The V are called eigenvectors. And by how much it gets scaled, lambda, that also is unknown. You have to figure it out. That is called eigenvalue. So this is a pair. Eigenvalue and eigenvectors are a pair. Okay. Given a matrix, you need to find set of vectors which only get scaled. Those are the eigenvectors. And by how much they get scaled, that's the eigenvalue. Okay. So pure stretching exercise. You have to find out the direction. Given a matrix, in what direction the matrix only scales the vectors in that direction. So that's very, very interesting. And note one thing, it is a very trivial thing. Once you find a direction in which vectors get scaled, there are actually infinite number of vectors that you can have in that direction. All of them get scaled. Okay, so see one thing. If AV is equal to lambda V, I can simply multiply 2 times V equal to 2 lambda, scale, if you scale that vector, scaled vector also is in the same direction. So that will also be stretched. So lambda times 2V, can I do that? Instead of V, I'm using 2V. Okay, so all of these, so the exercise is to find the direction actually. It is not the single vector because any vector in that direction will also be scaled. Okay, so what is the direction and what is the scale factor? Two things. What is the direction? What is the scale factor? So eigenvector, eigenvalue. And it is not necessary that there is only one direction. There could be two directions. This is one direction, this is one direction, maybe. So all vectors in this direction also get only scaled by this transformation. Okay. Now, eigenvalue, eigenvectors are extremely important. Let's look at the maths, and I'll also show you. I'll prove geometrically that this is exactly what how it is working. So, how do we find out the eigenvalue and eigenvectors of a matrix? This is the last topic for today. So, we have this fundamental equation, right? You are given A, you want to figure out V and lambda such that A times V is lambda times V. Please note that lambda is a scalar. So multiplying a matrix with a vector results only in scaling the vector. Now, I can multiply, so I can write V as I times V. I is identity matrix. Okay, and I shares the same size as A. See, I can take I as anything. This is I. This is I. It's a 2 by 2 I, it's a 3 by 3 I. So depending on whatever A is, I can take the same size I. Actually, V's dimension would also match with, remember the number of rows would match. Okay, so the same dimension I'll take for the identity square matrix. So no issues writing V as IV does not, multiplying I does not change V, so I can write that, right? And take this one to the left hand side. We get this equation. A minus lambda I whole times V is equal to 0. Now, this is also a matrix. Correct? Matrix subtraction A minus lambda I. Now, here is the thing. This matrix is multiplied with vector V. See, this is the original equation. I got a different type of equation, which is more interesting. This matrix multiplied by V makes it 0. 0 means, see, 0 is in bold. It will be 0, 0, 0. Depending on the dimension, you get 0. Okay. Now we are looking for solutions. What are the possible V's and the associated lambdas? One trivial solution to this problem would be if you take V itself as 0, then you multiply any matrix times a 0 vector will give you a 0 vector. What's the big deal? Any matrix multiplied by a 0 vector will give you a 0 vector. Because 0 vector has no size. And no matter what you scale, what kind of transformation you do to a 0 vector, it will be a 0 vector. It's just a point. You cannot transform a point to become a line or anything. Its point will remain as a point. Okay. So one trivial solution to this equation is a 0 vector. But we are not interested in that. We know that 0 vector will get scaled by, well, doesn't matter. You can scale the 0 vector by anything, it remains as a 0 vector. We are not interested in this solution. We are looking for other solutions other than 0. Okay. Now, so if this solution is, now remember, there are multiple possible vectors that will lead to this solution. So if the solution is not unique, there are other solutions, right? If it is a case of infinitely many solutions, there exist infinite such vectors for which this is satisfied. Okay, so if the solution is not unique, that means there are infinitely many solutions, then the determinant of this matrix would be 0. Correct? Determinant of this matrix must be 0. And that gives us the characteristic. This is called as the characteristic equation of A. So in order to find out, so I'm summarizing, in order to find out, so what is, first of all, what is eigenvector, eigenvalue of a matrix? It is those vectors which only get scaled when you multiply the matrix to the vector. And the scaling amount is called the eigenvalue, and the vectors are called eigenvectors. In order to find those vectors and values, we developed a characteristic equation for A, which is given by this, which is determinant of A minus lambda I equal to 0. Okay, now let's take an example and understand how this works. I've already done it here, so we can just walk through this. So let's say this is our matrix, 2 by 2, simple matrix. We want to find out the eigenvalue and eigenvector for this matrix. This is our main equation, right? Which vector gets only scaled by this matrix. This is the second equation, right? Which is the homogeneous equation. Now, in order to have to solve for eigenvalue, eigenvectors, you have to write the characteristic equation. This is called the characteristic equation of A. Well, let's write this. So this is A, correct? Original A minus lambda times identity vector. Just match the dimension with A. Okay. And this is easy. So look at the diagonal. So this 2 minus lambda, right? 1 minus lambda times 0 is 0, 1 minus 0 is 1. 1 minus again 0 is 1. And 2 minus lambda is here. Okay. Determinant of this matrix must be 0 because we are looking at infinitely many solutions. So what is the determinant of this? Determinant of this is 2 minus lambda whole square, this minus 1 equal to 0. Are you with me so far? We are solving the characteristic equation for the matrix. Cool. So this is a quadratic equation. It will have two solutions. That's nice. I open this up. Lambda squared plus 4 minus 1 is 3. And then minus 4 lambda is here equal to 0. The roots of this equation are 1 and 3. These are called eigenvalues. So we solved for the eigenvalues uh, already. Okay. So we don't know the vectors yet. We'll figure out the vectors, but we found that there exist vectors, okay, which are scaled by 1, which essentially means the vectors don't even change, they remain as is. See, this matrix is not identity matrix, but there are vectors, I mean, there are specific directions in which there is a stretching of a factor of 1, which means the vectors don't even change. And there is some other direction along which all the vectors get stretched by or scaled by 3. This matrix causes that kind of transformation. So we solve the eigenvalues first by solving the characteristic equation. Next step would be to figure out the associated vector directions. In which directions vectors get scaled by 1, in which direction vectors get scaled by 3. How do we solve this? Is very easy. So first case, lambda equal to 1. Just put it in this equation, okay? If you put lambda equal to 1, what does a minus, look at this equation. What does a minus lambda I become? A minus lambda I is this. 2 minus lambda is 1, 1, 1. Again, 2 minus lambda, it's 1, right? We know that a minus lambda I times v, now I'm assuming v is xy. A minus lambda I times v equal to 0. That is what this equation is all about. I know lambda is 1. One of the values of lambda is 1. So I'm solving it. If this is equal to 0, you will see. Now, this is very, very interesting. It's trivial. Determinant of this matrix is 0 by design because I made it 0. The determinant of a minus lambda is 0, right? So you can cross check that the determinant is still 0, right? It needs to lead to infinitely many solutions. That means you will have the same equation twice. Just look at this. So if you multiply, what you'll get? X plus y must be 0. Two equations emerge. Just multiply. X plus y equal to 0. And the second one, again, x plus y equal to 0. Do not get surprised when the equations repeat because we want to have infinitely many solutions. This is by design. It's not a unique solution. Okay. So that's why you only have one equation. Out of two system of linear equations, you have one, essentially one equation. So what do? Do not worry about the second equation. It's just repetition, right? So we have this x plus y equals 0, which essentially leads to a set of vectors, infinite set of vectors. Whichever meets this condition are part of this group, okay? So any vector you can imagine that satisfies this condition. So simple example would be 1 minus 1. X plus y must be 0. You can take 2 minus 2 also, doesn't matter. The convention is when you report eigenvectors, one of them should be 1, right? You can just make one of them as 1, the other one comes out as minus 1. That's your eigenvector. Please remember, direction is important. This direction, any vector in this direction will be scaled by 1. Any vector in this direction will be scaled by 1. Minus 1 minus 1, 2 minus 2, anything. Okay, 0.5 minus 0.5, that also works. But when we report, softwares will report it like this, 1 minus 1. Okay, let's look at the other side. Lambda equal to 3. This matrix becomes 2 minus 3 is minus 1, then 1, 1, minus 1. Check the determinant, still 0. Minus 1 times minus 1 is 1, 1 minus 1 is 0. And I'm solving for this equation, a minus lambda I times x is equal to 0. The system of equation is minus x plus y equal to 0, x minus y equal to 0. It's the same equation. Same equation. X equal to y. Any vector that has both components same, x equal to y, are that family, that direction. Okay. So my answer would be 1, 1. Is the standard choice. This is my eigenvector that will be scaled by 3. You can take any vector, 2, 2 works. Okay, so my final answer is eigenvector is 1 minus 1, eigenvalue is 1. Eigenvector is 1, 1, eigenvalue is 3. For this matrix, you only need the matrix to figure out what are the directions and what are the scaling factors. Eigenvector, eigenvalue, clear? See, these kind of material is abundant in online literature. You'll find exercises, plenty of exercise in any website, anywhere. So if you want practice, I would suggest go to any, just Google exercises on eigenvalue and solve the problems. I will share some, but yeah, I mean, it's common knowledge. Okay. Geometrically, do you want to see how this works? I'll show you. Since we have the Excel, what is our A? 2, 1, 1, 2. Okay. 2, 1, 1, 2. This is the kind of transformation it does. Okay. 1, 2 vector becomes 4, 5. Can you tell me if it only gets scaled or also it gets rotated? Or I mean, it's mixed of. Okay, is this the vector that only gets scaled? That's my question. Would this be a vector that only gets scaled when I multiply a with x? No, right? Because 1 times 4 is 4, but 2 times 4 is not 5. So, but we figured out vectors which will only get scaled. The first vector is 1 minus 1. Let's see. 1 minus 1. Now look at this. Original vector is 1 minus 1. This matrix got multiplied with this. What is the final vector? 1 minus 1. What is the scaling factor? Direction has not changed, obviously. But what is the scaling factor here? Scaling factor is 1 because 1 minus 1 multiplied by 1 is same, 1 minus 1. And that is lambda. Lambda equal to 1. Remember, scaling factor equal to 1. So any vector you take in this direction does not change, remains completely intact, which is nice. So I can take maybe 5 and minus 5. No change in the vector. Direction remains intact, scaling factor is 1. That's one of the eigenvectors, and the corresponding eigenvalue is 1. Let's look at the other direction. The direction is 1, 1. That means x equal to y, right? Scaling or stretching factor is 3. Let's see. So we take 1, 1 becomes 3, 3. You can see the orientation, the circle has become the ellipse. And it's a stretching in this direction and this direction. So in this direction, it has retained the same size. I mean, the circle radius is same here. But in this direction, this stretching, right, it has become 3 times. That's it, right? So in this direction, all vectors get stretched by a factor of 3. 2, 2 becomes 6, 6. All right. What does minus 1 become? Minus 3, minus 3. Okay. Now, any questions on eigenvector, eigenvalues? Clear. Perfect. I think last slide. Yes. A very, some very important properties of eigenvalue, eigenvectors. We will use it sometime later. Few of them, not all of them. We have something called, something called as trace. Trace of A, any matrix, the trace is the sum of the main diagonal entries. Sum of the main diagonal entries is called as the trace. Trace is same as sum of eigenvalues also. Trace is also same as sum of eigenvalues. That is really powerful. Is it true? Let's see. The matrix we have here. What is the trace of this matrix, guys? Trace of this matrix is 4. What are the eigenvalues we computed? 1 and 3. 1 plus 3 is 4. That's the theorem. Okay. Trace is sum of eigenvalues. That means if I give you a 100 by 100 matrix, 100 by 100 matrix, I give you the full matrix, okay? And I give you 99 eigenvalues. And I ask you, hey, what is the final eigenvalue? You can calculate. They get this sum and take the difference. Okay. Next, determinant of A is product of eigenvalues. How beautiful. In our case, what is the determinant? 4 minus 1, 3. And that is 1 times 3. Okay. Determinant is product of all eigenvalues. That's why, oh, I haven't explained. Okay. Uh, so if it is a product of eigenvalues, okay, then if one of the eigenvalues is 0, eigenvalues is 0. It's possible. If one of the eigenvalues is 0, that means determinant will become 0, which means it is not full rank. All of these are connected. Okay. If one or more eigenvalues are 0, determinant becomes 0. If determinant becomes 0, it's a singular matrix or not full rank. Cool. Next, eigenvalues of a to the power k, so a matrix multiplied by itself k times, is kth power of the original eigenvalue. So if I take the matrix we had A, right? If I take A square, the eigenvalues of A square would be 1 and 9. All right. Next, A is invertible only if all the eigenvalues are non-zero. This is actually related to one of the other theorems that we just talked about. Which one? You can prove this using which line? A is invertible only when all eigenvalues are non-zero. Remember invertibility condition. Inverse exists if determinant is non-zero. And for determinant to be non-zero, you need all eigenvalues to be non-zero. If one of them is 0, then determinant is 0. Matrix is not invertible. Eigenvalues of the A inverse are reciprocal of the eigenvalue. So if I give you the A inverse matrix and ask you what are the eigenvalues, you can confidently say it is 1 and 1 by 3. Because eigenvalues are also the reciprocal of. So eigenvalues are so fundamental, right? Eigenvectors, remember, of a symmetric matrix are orthogonal. Eigenvectors of a symmetric matrix would be orthogonal. That means 90 degree. So, right, the vectors would be perpendicular to each other. Eigenvectors will be perpendicular to each other for a symmetric matrix. Okay. Eigenvalues of a positive definite matrix are, so when we talked about positive definite matrix, remember this was the definition: X transpose A X greater than 0. Take any vector X, transpose times A times that vector. If it is always greater than 0, then we say A is positive definite. The other way of how do you verify this? It's very hard. Like how do you have to prove this? Take any random x and prove using algebra that this is always greater than zero. Normally, it becomes square of something and then plus something. So we prove that it's greater than zero. The easier way to prove this is just take A. If all the eigenvalues are greater than zero, it is positive, definite matrix. That's easy, right? Just calculate all the eigenvalues. And if they're all positive, then the matrix is positive, definite. Finally, same thing. So eigenvalues of a positive semi-definite matrix will be greater than equal to zero. So if some of the eigenvalues are zero, none of them are negative, then we can say matrix is positive semi-definite. Okay, so this is an easier way to prove whether a matrix is positive definite or positive semi-definite by purely looking at the eigenvalues. Yeah, that's all I had. All of these are just one-line functions in Python, so you'd never have to calculate it by hand. But fundamentals are important, okay? All right, that's all I had. Any questions before we wrap up? Did you enjoy the session today? Cool. All right, I'll see you next week. Thank you. Bye-bye.